Good afternoon, everybody. We're going to start the class today on finding the roots of equations. So last week, we started with finding the roots of equation. Then we did the bisect method and the first position method. So we are going to start with the class today. But before we start, I just want to make mention of what we did last week. So there was a question that a student asked me that, how about if, can you define the variables or the parameters within the code? So we tried it during the class, but it did not work. And so I actually did it again. So the reason why there was an error was because of this is the lower limit and this is the upper limit. So I set the lower limits and the upper limits, I set them as integer. So that was why it was given some kind of variable data type error. So now when I change it to double, it's got working. And the reason for that error is because even though they are integers, like 12 is an integer, it doesn't have a decimal part. And 16 is an integer also, it doesn't have a decimal part. The reason why we needed to set it as double, which has decimal parts, is because when you need to keep calculating the lower limits and the upper limits. So at the first iteration is an integer, but when we get to the second, third, and fourth iterations, they will become double. So it's going to change, the data type is going to change to double because you will start having fractional parts. So the best thing was for us to define it as double because during the course of the iteration, is going to change to double. So that's why the lower limit, I set it as double. Then the upper limit, I set it as double. So previously, I set it as an integer. So that was where the error came in. And I told you that in Visual Basic, when you have a decimal or a double data type, you can say 0.0. And when you put 0.0, Visual Basic is automatically going to change it to hash. So I put 0.0. So when my cursor leaves to another line, Visual Basic will change it to hash. So that's the representation in Visual Basic. And the others are the same thing. And if you go to Excel, since we've defined the parameters here, if you go to Excel, all you just need to do is to call in the bisect method or the bisect function without no parameters. So when you do it, since you've already defined the parameters within the code, you don't need the parameters anymore. So you just call it this way. So that's that about what we did in the last class. But like somebody rightly mentioned, when we started, when the danger of doing it this way. So the danger of doing it this way is that when you want to change the parameters, because you have 4 parameters. Let me go back to the share. So we have 4 parameters. The first parameter is the lower limit. The second is the upper limit. Then this is the error. So the danger of doing it this way is that when you want to change the parameters, you have to go back to the code and change it. But if you had done it the other way that we did it, you don't need to go back to the code to change the parameters. So you can just change it on Excel or the Excel worksheet. You don't need to change it on Visual Basic application. Okay, so we're going to start the lecture for today. So the lecture for today will still continue on the roots of equations. So in the last class, we did bracketing methods. Bracketing methods are those methods in which you want to get the roots, but you have to specify a lower limit and an upper limit for you're going to approximate or you're going to guess the lower limit and upper limit. But in open methods, you open method is quite different. For open method, you just need a single value or a single guess. You don't need two guesses. And in cases where you need two guesses, those guesses don't have to bracket the root. We're going to be talking about more on that later. So the three methods we are going to be considering for the open methods are the simple fixed point iteration, the Newton-Raphson method for finding the root, and the secant method, which is also otherwise called the linear interpolation method. So we start with the simple fixed point iteration. In the simple fixed point iteration, when you are, I will just start with an example, but the first thing to note is that you just have one guess. This is in contrast to the bracketing methods where you have two guesses. So you just have only one guess. Then when you are giving, I'm going to explain it using examples. So for instance, if you're given this equation and you are asked to find the root using the simple fixed point iteration, all you're going to do is you're going to make x the subject of formula. You're going to make, there's a x here and there's an x here. You're going to make one of them, preferably the one with that is easier to make as subject of formula. So we decided to make x as subject of formula. Then, for example, so this is one example. If you are given this equation, this is how you make it the subject of formula. But in general, the way you specify the question is given by this x is equal to g of x. So if you have this function, you're just going to make one of this x, or you can also make this one, but the one that is simplest is subject of formula. In the case where you are given an equation of this form, because here there are two x's, there's one x here and there's one x here. But in this case, there's just a single x. So the way you do it is that you are going to add x to both sides of the equation. So the new equation is going to become this. So in case where you just have just one x, you would add x to both sides of the equation to give you the new equation. Then the formula to predict a new value of x is given by this. So the next value of x, okay, I think there's a question. Okay, I'm on the road traveling. What? Okay, all right, okay, I got that. Okay, in case you have any questions, just type it in the chat. Then I would look at it from time to time and I'll try to answer. In this case, so like I said, after you've defined it in this form, you're going to, okay, another question. We derived V in the class to be in the textbook was, okay. Okay, that question was for the first class. So probably after the class, I'm going to answer Sukomi, your question. You are dragging us back. I'm going to answer you. Send me a mail about that. I would answer you. So Samson said in the first equation, x is equal to s squared plus 3 over 2. Okay. X is equal to s squared plus 3 over 2. Okay, you're right. So it's supposed to be, x is supposed to be equal to equal to x squared plus 3/2. Okay, so thank you. Thank you for that correction. So this was supposed to be the equation. So thank you for that correction, Samson. Okay. Um. So after you get the formula for x, so you're going to predict the next value using this equation. You're going to predict the next value using this equation. Then this equation says that the next value, I plus 1, is equal to g of x. So in order to understand it better, we are going to do an example. But in the case, before we start with that example, in the case of this, the next value is going to be xi plus 1. Xi plus 1 is equal to xi is equal to xi squared plus 3/2. That's how you're going to predict the next value for this. Then in the next value for this, it's going to be xi plus 1 equal to sine xi plus xi. Let's do an example. So the first example is this equation. So you're going to find the root employing an initial guess of x naught is equal to 0. So like I said, for open method, it's just one guess you are giving. But for the method we did last week, you are giving two values in which you're trying to get the root. But in this method, you're just giving just one guess. So this is the equation here. Then you're going to make x the subject of formula, like I said. So we just say that we'll bring x to this side. So we say that x is equal to exponential minus x. Then the way we predict it, you say that the next value of x, or the next root, or the predicted root, is equal to exponential minus xi. So the um the predicted root is going to be exponential x, and this x is the current value or the previous value. So you can say that the current value is going to be a function of the previous value. That is the way we're going to do that. So in solving that, we are going to, I just did it in form of a table. And like I said, I'm tracking the error. Like I told you, numerical methods are approximate errors. So definitely there are going to be errors. So you need to track it. So you're going to start with x naught is equal to 0. So this was the value we're giving. So we have different values of I from 0 to 10. So I decided to start with 0 because I'm starting with 0 because the initial guess is that at I is equal to 0, x of 0 is 0. So that's why you have to start with that. So when I is 0, x of 0 is 0. So we're giving this. We're giving this in the question. So to move to the next value of x, which is x1. So x1 is simply the exponential of x naught because x1 is the new value. Then I equal to 0, x naught is the previous value. So you keep on going. So x2 is equal to exponential minus x1. x3 is equal to exponential minus x2. x4 is equal to exponential minus x3. So you keep on going like that till you stop at uh, wherever you want to stop. So we're given this. This was our initial guess. So when you do the exponential of -0, this 0 came from here is 1. So for the second iteration, you want the exponential of minus x1. We got x1 as 1. So the exponential of -1 is this. For the third iteration, you are doing the exponential of minus x2. So we got x2 here as this. So the exponential of minus x2 is this. So you need the previous value in order to calculate the current value for this method. So we decided, so you keep on doing it, and at the same time, as you move on to the next iteration, you need to track the error, because it is the error you're going to use to determine when you are going to stop or not, or the number of iterations. So we want to track the error. So the estimate error, remember that estimate error is the current approximation minus the previous approximation divided by the current approximation. So here we just started, so we don't have a previous approximation. So we just left it empty. Then the true error, if you can remember, the true error is the true value minus the approximation divided by the true value. So the true value is given as this. So from there, you will track both the estimated error and the true value. So as you move through the iteration, so when we got to the 10th iteration, we got the estimated error as 1.1, then we got the true error as 0.399. So we can see that the error is reducing. So at the 10th iteration, we add this value. So if you want to stop at the 10th iteration, that means that the root of this function, of the question we started with, the root of the question we started with is given by the value where you stop. So we are stopping at the 10th iteration. So this is your estimated, your root when you stop at the 10th iteration. And the error at the 10th iteration is 0.33. So if you want a better approximation of the root, you can go on in order to reduce your error so that you will be much more accurate. So there is a question: is it the true value given to us, or we are to find the true value first using the graphical method? Okay, thank you for that question. The answer to your question is that, okay, your question is that the true value, how are you going to get it? Because if you want to track the true error, the answer to your question is, if you can either use like we did when we're talking about errors in mathematical approximations, you can either use the estimated error or the true error. And the true error is the best approach to finding the error. But like I told you, there are some instances when you you don't know the true value, so you cannot calculate the true error. So you have to go with the estimated error. But in the case where you are being examined, if you are not giving the true root, just you don't need to do the true error, because you need the true value in order to calculate the true error. So in the case of an exam, if you're not giving the true value, then that means that you should not, there's no way you can calculate the true errors. But at the same time, you can calculate the estimated error, because the estimated error is the difference between the current approximation and the previous approximation. So the answer to your question is, if you're not giving the true value, just ignore the true error. Just go with the estimate error. That's what you should do. The true error, it represents the true, like it is the correct error, but the estimate is just an estimate. That's where you don't have the true value. So I think there is a question. Was the true value being given, or we found the true value of the function solving it analytically? Okay, I already answered that. So John asked a similar question, and the answer is that if you are not giving the true value, if you are not giving the true value, then don't bother don't bother trying to solve it. Don't bother trying to solve it. And that means that don't bother getting the true error, because you need the true value to get the true error. So just go with the estimated error. So if if you the answer is, if you are not you'll be given the true value, but if you are not giving, that means that just work with the estimated error. So we are going to use we're going to program what we did here using Excel VBA. So we want to use the fixed point iteration. We want to use the fixed point iteration to get the root of this function using the simple fixed point iteration. So let me go to Excel. Let me go to Excel VBA and share my screen. Okay. Okay. So let me share my screen. Okay, so this is the Visual Basic Visual Excel VBA code to do the same thing. So we did the question by hand. So now we are doing the question using, we're writing a computer program to do the question. So now this is the name of the function, fixed point. The function is taking three parameters, x0. X0 is the initial guess. So like I told you previously, so the parameters here are what you are going to specify. So you are given the initial guess, then the estimated error is the error in which you want to stop, or when the error you are calculating, when it's less than the estimated error, then you should stop. Then Imax is the maximum number of iterations you want to go. So you're going to specify this. You specify the estimated error, and you specify the maximum number of iterations. Then this is the function. Then you define the variables. Then this line is saying that let the initial guess be equal to the root. Then you set the iteration to 0. Then you keep on, at this point, you keep on implementing the iteration. Then this function g of x, this function is the question you are giving. Remember, the question was x is equal to exponential x. So we are saying that the question is x is equal to exponential minus x. So this represents the return type of the function. Then you are simply calculating exponential minus x. So it's at this point, the name of the function is g. So it's at this point you call the function. So the new value of the root is equal to a function of the old value of the root, then this is where you're going to calculate the estimated error. And this is your stopping condition. So you stop when the current error is less than the estimated error. So this estimated error is you're going to specify it. And the most important thing in this code is this. This is the most important thing. Yeah, so you're saying that the new value of the root is a function of the old root. So XR old is a function of the old root. And this function here is defined here. Then the function of the old root is exponential minus x. Then let me go to Visual Basic, Excel, the Excel worksheet. So this is, okay, sure. So this is the Excel worksheet. So here, in the question, the initial guess is 0, so x naught is 0. The estimated error, I just specified it as 0.01. Then the maximum number of iteration is 100. So when you want to call the function, you just call it with the three parameters. So the initial guess, the estimated, the error estimates, and the maximum number of iterations, which are given by this. Then when you type enter, it's going to give you the, the value of the root. So if I want to be much more accurate, I can improve my error estimate. Let me say 0.001. So if I do that, the true value of the root is going to be much more accurate. There is a question. For the error estimate, is there a standard value for it? Or it is being given? Okay. The estimate error is just, is you're not going to be in the question. If you are giving a question, you are going to be giving, like you can say that you want your estimated error to be less than 0.5. You can say that you want it to be 0.5 here. So if you are giving a question can say that, okay, calculate the value of the root when the estimated error is less or equal to 0.5. So you just put 0.5 here and you're going to calculate the root. But when you're doing the design on your own, it's less for you to take the initiative. Like if you are doing it on your own, then it's left for you to specify it. If you want the estimated error to be less than 0.1 or 0.01, or so it keeps changing to a much to a more correct value, or you can say 0.0001. It will keep on changing that way. So it's left for you. So if you are giving a question and the question is forcing you that your error should not go beyond a specific value, then definitely go with that. But if you are doing it on your own, then it's left for you to specify the uh, the estimated error you want to set. So like somebody asked in the other class, so these values, yeah, we got it from the Excel worksheet. But if you want to put in these values in the code, then you just do it similarly to the way we did it previously. So that means that there's no need for all this. And that means that you need to specify all this in the code. But uh, the downside to that is that the downside to that, so it's supposed to be x0, then ES, then IMAX. So the downside to that is that you wouldn't be able to, you're not so flexible. Like when we wanted to change this, if to say we'd specified it in the code, we had to go back to the code to change it. But now that we just specified it in Excel worksheet, we know that anytime we write the code, we know that we are done with the code and we just focus on the Excel worksheet. So that's that for the fixed point iteration method. So let's go back to the note. This is the code, the one you want to call it, like I said, you're going to call it in this way using the three parameters. So the next one we are going to consider is the two-curve graphical method. So this is a graphical approach to finding the roots. It's just that it builds up from this method we've used previously. So in this method, when we wanted to use it, so this was the question. So when we wanted to use it, we made x the subject of formula and we got this function. Then after that, we used the method. So in the two-curve graphical method, what you are going to do is that you are going to plot this function here, the function on the left hand side. And you are going to plot this function on the right hand side. Then the point at which this function and this function meet, that is the root of the equation. So that's the two-curve graphical method. So I'm repeating it. In the two-curve graphical method, you are going to plot this as a function of x. You also plot this as a function of x. The point at which the two curves meet is the root of the equation. So let me go back here. So this is the two-curve method here. So before that, you know you are plotting the left hand side, which is x, and you are plotting the right hand side, which is exponential minus x. So you need to get x at different values. So we said 0 to 1. Then we need to get you need to get the function of x. So it's simply this column here is simply this column. Then you simply get exponential minus x. So exponential minus 0, exponential minus 0.1. So this is simply exponential minus x. Then you have the values. Then when you plot it, you're going to plot this as a function of x. Then you plot this as a function of x. So this is the plot. So we are plotting this, the first one as a function of x. Then you're plotting the second one as a function of x. So the point at which they meet is the root. So if you trace it down, is about 0.57. And this two-curve method is just another method. So last class, when we did the graphical method, for the graphical method, all you are going to do is that the function, which is this exponential minus x minus x, so you're just going to plot it like that using the same method we used last week. So if you use that first method we used last week, this is going to be our graph. Then, like I told you, the point at which the line touches the x-axis is the root. So it touched the x-axis at 0.57. So the two-curve method, so this is for the two-curve method, two-curve graphical method. Then this is the original method we used last week. So they are both going to give you the same result. So this point here, where they touch, when you trace it down, is 0.57. Then the point at which this curve touches the x-axis is also 0.57. So this method here is just building from um, the fixed point iteration method. Is going to give you the same method as the one we used last week. So we move on to the Newton-Raphson method. So I'm going to end the meeting. I'm going to end the meeting now because of the time. Then you join using the the same link. Okay, there's a question, meaning that there is no difference between between the curve graphical method, the two curve graphical method and the graphical method. Yes. Um, the answer to your question is both of them are different. There's a difference. For the graphical method, you are going to plot the function. In this case, the function is exponential minus x. So this is the function we are plotting, exponential minus x. So in the graphical method, this is what we are plotting. But in the two curve method, in the two curve graphical method, you are plotting two curves. The first being the function on the left-hand side, then the second being the function on the right-hand side. So the point at which these two curves meet, that is the root. But for the graphical method, it is the point at which the curve touches the x-axis. So here is the point at which the two curves meet. That's the root. But here, it is the point at which the curve touches the x-axis. That's the root. So that's the difference. They are different, but you're going to get the same value. They're not the same thing. But at the end of the day, you would still arrive at the same value.